The Higgs particle to most people is a rather mysterious thing. They don't know very well what it is for. And the talks that you get sometimes are, well, in my point of view, simply falsified. It's not the real reason. So I have in mind here to try to give you the correct way of talking about the Higgs, what it does, and what we actually do with it. Now, we start off with the self-energy of the electron. The electron is a small particle in which charge, as far as we know, is concentrated in a point. And now the first thing that happens is the first time people got confronted with this particular difficulty of the theory. The energy, it's about the self-energy of the electron. And in 1904, there came for it the theory of Abraham and Lorentz. Mind you, this was before the theory of relativity, which is from 1905. Yeah? And the theory of Abraham and Lorentz is one whereby the electron was made into something which was a small sphere. Yeah? And the way you thought about it is like this. You think of the charge of the electron spread out over all of space, and you assume that there the energy associated with that is zero. Then you start compressing all that charge into that little sphere, and in order to do that you need to exert energy, and this is the self-energy of the electron. And if the sphere becomes a point, that energy goes to infinity. And in fact, the correct equation is that the energy associated with that small sphere is 1 over the radius of the sphere. It's proportional to that. So if you compress it twice as much, the energy goes up by a factor of 2. And that was the first attempt by Abraham and Lorentz to get hold of the self-energy of the electron. And of course, what you see here is by the time you get to be a point particle, the energy is simply infinite. So the fight of the self-energy of the electron is a fight for the infinities. There's infinities coming up in the theory, and people did not really know what to do with it. So the smearing out of the charge to a finite volume, let me just give you the name, is a method, is called a regulator mechanism. I make something which is finite, infinite. The electron, the point electron, I make it in a volume, thereby it becomes finite, the energy associated with that. And so that's the
I just want to write down something.
Yes. So that's what happened there. Here you have the elements that have remained with the theory for quite a long time. You have an infinity, and to what you understand, the electron being a point, what you do is you change it a little bit. It's called a regulator mechanism. In this case, that's the little sphere. Yeah. And that regulator mechanism, well, that's what you need. There's little you can do about it. So what do you do about it? This remained. Progress in this business was really slow, and it took another 35 years before we finally got some more hold of it. And here you see a picture of Mr. Abraham, who was an astute young man. He was very stubborn, and he was very much, well, never mind. And Mr. Lorentz, that you may have heard of. And they were the two that made it. And Lorentz, as well as Abraham, died before he got the next development of that situation. The next development of that situation was born, of course, with quantum mechanics. Quantum mechanics changed everything. And the people who made quantum mechanics, Heisenberg, Schrödinger, they changed everything. But the first version of quantum mechanics, with Schrödinger and the like, from 1925, was a form of quantum mechanics that was capable of telling you the energy levels of an atom, but it could not describe the mechanism whereby an excited hydrogen atom could fall down to a lower level and emit a photon. So the emission of a photon, that stuff was not contained in the first form of quantum theory. That came somewhat later. That was then called field theory. So quantum theory had to be enlarged, made bigger, in order to allow for the fact that the photon can be emitted. Yeah. And that was mainly done by the people that you see here. Well, there's three of them. There's Heisenberg and Pauli. They started with a subject called field theory. And then there is Weishaupt, who was the first to attack the problem of the self-energy of the electron once more. And he discovered, that was at least one step forward, that the energy, the self-energy of the electron was something that was still becoming infinite, but within the framework of quantum field theory, it went only like the logarithm of that radius of the thing. Yeah? Well, it was not the radius, but it was somewhat better. Still, it was bad. And now quantum field theory was created in 1929, and the story is really a slow one. It took all these steps, which were by themselves not that big. They took a long time before we got around to it. And so in please sir, take my chair there. So here you see a situation. Here you see what I mentioned. It's still divergent, the self-energy of the electron. And here I have introduced a concept which is called the Feynman diagram. That's an illustrative way of picturing what's going on. You see there an electron coming and it emits a photon and reabsorbs it later on. That's an interaction with itself that takes the place of the self-energy in the classical theory. So, and the divergence of that situation is logarithmic. So there is progress from the linear of Mr. Lorentz and Mr. Abraham with the little sphere. Now it has become logarithmic. And that's because you do, it's a bit of a trick, you do symmetrical integration and then the linear part cancels out. But anyway. Now, you see here the following so far. If you want to deal with infinite objects, then you have to invent a way to make them finite. And in the case of Lorentz and Abraham, you make it finite by smearing the electron over a small volume. Yeah. And then, once you have done that, so you have to invent a regulator mechanism. And then you must take the limit, take the limit to reality, that is what you think is reality, namely the electron, in this case being a point particle. So you give that you have to do it all the time. But now there comes a new complication that is also difficult to deal with, and people just didn't recognize those things. As I say, it took a while to do it all. The regulator mechanism should respect important properties such as Lorentz invariant. You don't want the self-energy of the electron. If the electron is a little sphere, you realize that in the theory of relativity, and you move an electron, it becomes an ellipse, because the length of the thing, well, it contracts. Well, it becomes a flat sphere. So that is no more the same. So the regulator mechanism, you must take care that it does not violate Lorentz invariance, that it is not something that goes against the principles of general relativity, that the moving frame should be not different from the frame at rest. Yeah. And there is another important property that is much more subtle. It has to do with the conservation of electric charge. Yeah. And now, in quantum electrodynamics, the fact that charge is conserved is usually expressed as gauge invariance. That was introduced by Mr. Lorentz. You have the gauge invariance of quantum electrodynamics, or from electrodynamics, and that guarantees you conservation of charge. Well, you must be careful that your cutoff method conserves charge. You should not, if you take the sphere and take a little bit away, at the same time take a little bit of charge away. You must not do that. Okay, so there's another one of these complicated things. And so Pauli and Villard, of course, they understood that perfectly well. And they developed at that time, which was quite early in the game, but still, I think it was still before the war, they developed a regulator method for quantum electrodynamics that respected gauge invariance and Lorentz invariance. So that was one step forward, but the subject remained a very complicated one, hard to explain to your neighbor, So that was then. And then there was the great revolution of 1948. The revolution of 1948 had to do with the effects of new experiments coming in. There was the lamp shift, and there was the anomalous magnetic moment of the muon, and these were effects, quantum effects, that were not given by the normal form of quantum field theory or by quantum mechanics. You had to do field theory. You had to start speaking in emitting particles, photons, reabsorbing them. And that got very complicated, so people realized you had to do field theory to explain those effects. So to put it differently, there came experimental results which necessitate the introduction of field theory, and which then in 1948 is what happened. So that was the lamp shift and the anomalous magnetic moment. And everyone felt, there was a conference at that time at Shelter Island near Brookhaven in the neighborhood of New York. And all the participants there were discussing these new experiments and the result. And the general feeling was, we have to do something about quantum mechanics. But what? The trouble is, when you were busy with field theory, as created by Pauli and Heisenberg, you got infinities all over the place. So it's very, very demotivating if you're busy calculating and you cannot go ahead because there's an infinity coming up. Nature is finite. But then there came Mr. Kramers, who was a professor in Leiden. He came with a terrific idea, and that was the idea of renormalization. He realized something that people had not realized before. It was a very simple idea, like there are so many simple ideas that you never know. And that goes about the electron self-energy. You see, the electron, we picture it as something which has electric charge. And the way we think about it is the electron has self-energy. That is to say, it's the electric charge that you press together that you call the self-energy of the electron. Now, the electron may also have energy of its own. It has a mass, so it could have a certain energy. So what happens is that the mass of the electron that you observe finally is the result of two things, the addition of two things, namely the mass that you start off with, plus the self-energy that is generated by the electric charge. So the experimental mass, such as we see it, is the bare mass. That is the mass of the electron that somewhere has been chosen by God to be there. And then in addition you get the energy due to all these charges being compressed. And the sum of these two is what you experimentally observe. So Mr. Kramer said, well, let's do it like follows. Let's not try to understand everything. Let's just say the experimental mass, that's something we can measure. And God knows what goes on in the electron at small distances and the like. Why don't we just skip that part of the problem? So what Mr. Kramers did was, he said, okay, so the self-energy of the electron is infinite. Okay, so what we will do is we will start off with an electron with the opposite amount of self-energy. And so the only thing we can say is the sum of the two should be what we see experimentally. So there, everyone was sort of stunned by this idea. The idea that you make your quantities, your properties of the theory, you make them infinite, and then you cancel them so that you get the correct finite result. Well, that's one part of the trick. The question now is, and that's the important thing of the theory, after you absorb the infinity of the self-energy of the electron into its mass, in the way that I'm saying here, the question is, what happens to the theory altogether? And then in the case of Kramers for quantum electrodynamics in that time, it turns out there are two kinds of theory. That was a new concept that came in. And the two kinds of theory are this. You have infinities in the theory, and some of them you can absorb in the available free parameters. That's really the easiest way of putting it. The self-mass of the electron, the experimental mass of the electron, is an experimentally observable parameter. It has a certain value, which in the theory comes about by the addition of two infinities. So that was the idea. And the idea was also that maybe at some future time you will know more and you will know how to deal with those infinities. Maybe you will find a better theory when you go at small distances. Maybe something happens there. But we postpone that problem. All we are going to say is, whatever you do, in the end, the result for the mass of the electron is what we observe. And how that comes about, who cares? Now, then the next question is, once you have done that, if you have taken care of that infinity, is then after that the theory finite? So, if you see the mass of the electron as a free parameter, then you can see I have absorbed an infinity in that free parameter. So that's really the game. And now the question is, how many free parameters does a theory have? Well, in the case of quantum electrodynamics, I can mention some. One is the self-mass of the electron. The other is the coupling constant, with which the photon couples to the electron, or the electromagnetic field to the charge. That's another parameter, which indeed, when you try to calculate, is also infinite. And so there's a second parameter, and so on. You can think of more of them. And the question is, at some point, you have absorbed a certain amount of infinities into certain free parameters, of which, in any case, you have no previous knowledge, so that you have to choose them infinite to get the correct experimental answer. Well, okay, why not? So the theory got there. You can understand that people had some difficulty with this whole scheme, but in the end, what can you say? The question is, does it work? Well, that's the wonderful thing. Quantum electrodynamics, as known at that time, after you absorbed a number of infinities in the available free parameters, the rest became finite. You could calculate anything. Among others, you could calculate the lamp shift and the anomalous magnetic moment of the muon. So this process, which is called renormalization, invented by Mr. Kramers, immediately led to understanding quantum electrodynamics, with some corner of it containing infinities that you didn't need to worry about. Now, if a theory is in such a way that you can hide the infinities in the available free parameters, such a theory you call a renormalizable theory. And it is the great big concept that has entered field theory, and that was invented by Mr. Kramers. So the idea of Mr. Kramers made really all the difference. He made calculations were done by various people, Beater, Feynman, Schwinger, and Tomonaga, and they gave results that agreed with experiment. And the resulting theory that we got then was the renormalizable theory of quantum electrodynamics. And so that was a wonderful piece of progress. However, the most important result of that whole development was due to Feynman. The fact is that what Feynman did is he invented something that he called Feynman diagrams. And the Feynman diagrams, they are very intuitive and you understand them. It makes the calculation very, very easy. In other words, as he said, it's sort of a bookkeeping scheme. So when you hear Feynman, I remember hearing Feynman when he got the Nobel Prize, he said, what did I do? Looking back, what did I do? I invented a bookkeeping scheme. And it's true. But you see, the bookkeeping scheme can be very essential if you are standing in front of some obscure, huge theory. And that's the great advantage of Feynman, namely that he simplified the theory to the point that it became easy to use and easy to extend. That's what he did. So, as I say, Feynman all he said was coming with the rhetorical question, what did I do? Well, I can answer him just as rhetorical. What he did was a great thing. However, a complicated theory such as field theory simplification is very necessary and the key to further progress. So I would say the introduction of Feynman diagrams helped us going on. So then we got to quantum electrodynamics. That then became an official theory. And quantum electrodynamics has Feynman rules. I will illustrate them for you here. You can see it. When you scatter an electron of a positron you always depict by something the arrow going the other way. So what you see here is the process electron-positron scattering. As you see, it's very intuitive. And you exchange a photon. There is a precise calculational scheme. Once you have this diagram, you can write down an expression, compute a cross-section, and precisely say what's going on. And there are elements to this theory. There are a thing called a vertex and a propagator. In that diagram, you see there is the point where the electron emits a photon and the positron absorbs it, or the other way around. That's called a vertex. Yeah? And you have to specify what mathematical quantity is associated with it, the same with the propagator, and that's how simple the theory becomes. It's wonderfully simple. So let's try if we can do something with it. So the next thing you do is study then, what I've introduced for you before, the self-energy of the electron. And then you see that corresponds to this diagram. That is, here you have the electron, it emits a photon, which then gets reabsorbed, and this represents, in the scheme of quantum electrodynamics or field theory, the idea that an electron is sitting in its own field. And indeed, if you compute the contribution of this diagram, you get infinite. Yeah? And then you follow the prescription of Mr. Kramers. You say the real mass of the electron is the sum of that diagram, which in fact tells you the self-energy of the electron due to the electric field, and then the mass that you started off with, which is that little cross, and now you just take care that the sum of the two is finite, and whether the other two are infinite, well, that's life. So, if you can do that, and if that takes care of all your infinities, then you say the theory is renormalizable. So the subject of field theory came up with a new concept, a renormalizable theory, and there were those field theories which were not renormalizable, at least not at first sight. And of course, we all tried very much at that time. This was the time, I might say, that I got into the field, more or less, in around 1960. At that time, we all knew of the successes of quantum electrodynamics, but there was more going on into nature. In nature, what more was going on is the weak interactions. Yeah, here you see the Feynman was proud enough of his invention to have his van illustrated in this way. And so the next thing that we got onto, there were still some interactions in the world that did not fall under quantum electrodynamics, and the question is, what can we do with them? And the first one is neutron decay. Neutron decay is a neutron going into a proton, meanwhile emitting an electron and a neutrino. And at that time, quite quick in the beginning, one got the idea that there was a mediation going on by another particle called a W. So the neutron went into a proton, emitted a vector boson, as it was called, it was discovered it had to be a spin 1 particle, and it then decays quickly afterwards in electron and neutrino. It's one of the properties of weak interactions, of quantum mechanics, that you can have such a situation even if the W is a very heavy particle. If you make it live only short enough, you can actually do such a process. So when you see a thing like this and you say, hey, why can I have the W functioning there? Well, the answer is it can function there if it only does it quickly enough, then the uncertainty in the time gives you an uncertainty in energy big enough to allow the existence of the W for a little while. So that is what you got there. And this W, which we now of course know it exists, and which now we know that it is at least 80 or 90 times heavier than the neutron, as well as the proton. So it is really very heavy, and it lives only very short time there. That is a mediator between the interactions. So we get the theory that we get there was the one in which the W, an unknown particle, the W couples to all kinds of other particles. In this case, the W, as you can see, conservation of electric charge tells me it must be a W minus. The proton has a positive charge, and if the neutron goes into a W and a proton, it has to be negative. And then it can become an electron and a neutrino. And there were other processes like K-meson decay that you could also fantasize about for this W being there. And I remember when I entered physics, the W was the great unknown, experimentally so to say. It was an hypothesis, most of us believed in it, but that was about where it stood. Now the important thing is, if I have this W, can I make a theory of weak interactions? What can I do with the W? Can I make a consistent theory where I have these couplings? Well, the only guide in building a theory that we knew at the time was renormalizability. So the question is, can we make a renormalizable theory around the W? So we begin by assuming that there is some sort of an interaction between the W's, like this 3-point thing. So the W can, for a short moment, become a W plus and W minus, and you can start building a theory with that. And then you start making calculations, start looking at processes. One of the processes you can look at, you see here. And what do you find out? You find it's horribly divergent. The theory of weak interactions, that of W's, that's what you call the theory of weak interactions. That theory confronts you with infinities, you wouldn't believe it. It's really this one diagram at the face value. If you looked at it just like that, it was infinite, I believe. It diverged with some high power of the momentum, something like let's see, how much was it? No, there's one over there, 1, 2, 3, 4, it's something like 8-fold a divergence of lambda to the 8th, not even linear or logarithmic, no, the 8th power. So what was going on there was way horribly out of the possible. So the question is, the next step was, what can you do? When you look at it, you can of course start trying to absorb those infinities in the available parameters, but needless to say, by the time you start looking at this kind of abnormal behavior, that becomes a totally impossible enterprise. So the weak interaction theory.
5 minutes?
What 5 minutes?
Left.
You got to be kidding.
No.
In any case, I'm not talking 5 minutes. I'm talking till I'm finished.
Well, some people
You have nothing to do. You go to lunch.
Yeah.
We all go to lunch.
And then
Do you want to go to lunch not knowing what's going on? Okay, let's now look to the question is, what happens to the bad infinities that you can have? What will happen? So what you do, you start then playing another game. It's an interesting game. What you start doing is adding on a new interaction, and you try to do it in such a way that the infinities that this new interaction generates cancel some of the bad infinities that you had. Yeah? So you start complicating your life. Here you have something that goes wrong. Let's make something which is equally bad, but they compensate. And you're left with something. This idea turned out to be a magnificent idea. It worked perfectly. And in the case of the vector bosons, as you see here, the first thing we discovered is that you had to add a 4-point interactions. And then you could somehow manage for most of the infinities to go away. Practically all. Yeah? And you can really, as I see here, you can get rid of almost all infinities of the theory. Almost all. It's the almost, of course, which is the devil. Yeah? And a theory that you get in this way, in which you have an ensemble, a collection of interactions, each of which are bad, but when you make them together, they neatly work together so that the infinities disappear. It's sort of a miracle. When you look at that the first time, you think, my God. Huh? So, one infinity remained. And now, it results, among others, in WW interactions. And then it was discovered, and that took a while. I didn't think of it. I still consider myself stupid that I didn't. But we needed to get rid of other infinities then, in this case, of the last remaining little infinity. We needed to introduce a new particle, and then make that particle have interactions with the other particles, such as to generate again, once more, infinities, which then would cancel the bad ones. This, ladies and gentlemen, is the kind of diagram that you generate, that you see here, and this particle that we had to introduce in a very careful manner, such as to balance remaining infinities, is the Higgs particle. And all the talk that you have heard about the Higgs generating mass of everybody else and stuff like that, that's just so much irrelevant. This is what happened. The Higgs particle made the theory of weak interactions renormalizable. And if it is renormalizable, you can put all the infinities in a few parameters, coupling constants, masses, and so on, and then you can start doing calculations. So, due to the Higgs particle, we are now capable of doing calculations in weak interactions with charged vector bosons. And so, here I come quickly, nonetheless, to the end of my lecture. The conclusion of the whole affair is that the importance of the Higgs construction is that it makes the theory, the Young-Mills theory of weak interactions, renormalizable. Yeah. And in fact, at the time that the Higgs was discovered, that it was used for this thing, not even everyone knew. You see, Higgs invented this Higgs particle in a very different context. He was busy with superconductivity and things like that. You could say it's by accident that that same situation now was useful in the weak interaction, and certainly what I remember, I didn't know at all about Higgs and so on, and we just discovered that adding on the Higgs was what made the theory fine, and we are totally happy with it. But of course that's not the way how it went in the end. But these are my two heroes. There is Mr. Higgs on one side, which is in another field, in another context, invented his particle. And then Mr. Kramers, who advanced the idea of renormalization and made for us something that can calculate. I think I will give a little additional clearing up of the situation.
Microphone. Microphone.
Microphone.
Cannot be heard.
Yeah. The question is, I want to give you an idea about this Higgs and the role it plays, so that you get an intuitive feeling. It is not strictly true, but gives you a feeling. You see, when I scatter an electron of a positron, here they go and they exchange a photon. There's a force going on. Yeah? And there is a force between electrons and themselves and so on that becomes big when you come to very small distances. Yeah? And what does the Higgs do? Well, the Higgs is another force that you introduce, because the Higgs also couples to electrons and positrons. You have to do that too. Yeah? And what happens is the Higgs gives rise to a new force which comes into action only at very small distances. Distances in those things have to do with the mass of the particle. So the Higgs gives you the mass, gives you the range of that new force, the mass of the Higgs. And that doesn't matter too much as long as the Higgs is there. So it's for this reason that we could not predict from the theory what the mass of the Higgs should be. As long as it was there and started cutting off things at the right time. So the cutting off was this. There was as the electron and positron, or the electrons among themselves, got nearer and nearer to each other, there was a point where a new force started to interact. And that force was generated by the Higgs particle. And was chosen in such a way that when you went to smaller and smaller distances, the sum of the two was no more behaving in a bad manner. You had regulated the whole thing. That's the function of the Higgs. And of course, as I tell you, theoretically we couldn't figure out what the mass of the Higgs was. It could be anything, The theory didn't tell you. But luckily enough, we found it at CERN. At least we found the particle that seems to behave like the Higgs. And so it seems that the point of view that we had, and that's sort of a long way, and you should be careful about it. You start off by the W's, you start introducing that coupling, a complicated game called the Young-Mills theory of things cancelling against each other. There's a little one thing remaining, you introduce an extra particle, that's the Higgs particle, and in the end they find that particle. It was in itself, of course, a great triumph for the theory, and we could calculate many things. I think I'll leave it to this. If you have any questions, I'm happy to hear them.